picking back up where we left off moments ago, we looked at the limit of this rational function as we let our x variable run off to infinity and beyond. You get it. So the next example that we're going to take a look at is a very slight variation of this. It's one of those like blink and you miss it, kind of things. So instead of having the numerator term, as a quadratic, now we've got a cubic, 2x cubed plus 5 over the quantity 3x squared plus 1. Same principle is in effect, though. For really big values of x, adding 5 doesn't change much. It's actually even less impactful than it was before because of this cube, right? Plus 1, same deal. So write in, my twiddle. Like I said, it's, that's not standard nomenclature. Anyway, so we have 2x cubed over 3x squared, ignoring the lower power terms and focusing just on higher power terms. Again, we get some algebraic cancellation. That goes away. The catch is we've got 3 copies of x in our numerator. So again, this is not standard, notation. But so we have 2x over 3, or 2/3 times x if you want to rearrange it a touch. So the challenge you'll end up running into here is now as x gets bigger and bigger and bigger and bigger and bigger and bigger and bigger, 2/3 of x is still getting bigger and bigger and bigger, and it's just getting scaled down by a factor of 2/3. So 2/3 of a massive number is still massive, just slightly less so. And if you keep letting it get bigger, it's still exploding. So as it turns out, this thing is actually still exploding. We've just kind of scaled it down a bit. So this time around, this limit is actually approaching infinity. Now, again, you got to be a little bit careful in this instance because, like in the last example, when this was a square, whether I had x approaching positive or negative infinity really didn't matter because, the algebraic cancellation just left us with a constant 2/3. Here, if this were negative infinity and this were negative infinity, we have 2/3 x again. X is now we're feeding in really massive negative numbers. We're actually having this thing go off to negative infinity. So you got to be a little more careful with this scenario. Okay, so I'm going to make one last modification to this thing. So bear with me just a sec. That actually wasn't much erasing, but you get into a habit. It's probably a bad one. Like I said before, I really dislike jump cuts. Anyway, so now we're going to modify this thing one more time, like this. He's gone. So it's just 2x plus 5 up top and then 3x squared plus 1 down below. Same principle holds, though. Again, for really big x values, these two guys, they don't matter all that much. Cover them up or disregard them, however you want to do it. Most textbooks, the actual approach that they end up having you take in this instance is like factoring off the highest power of x so stuff cancels, and then you end up with a whole lot of 5 over x, 1 over x squared, and you kind of write off those terms as going down towards 0. But, it's there, but it takes a lot of breaking down, and I don't think it really, gives us much in the end game. Anyway, so we have the limit as x approaches infinity of 2x up top, 3x squared down below, and we're in a reverse of the boat from, what we just saw. This guy cancels out completely. We have 2 x's down below, so we're left with 2 over 3x instead of 2x over 3 by itself. Now, as we let x get bigger and bigger, and the top is just sitting there and not doing anything. It's just a 2, bump on a log, if you will. Down below, we let x get bigger, triple a big number is even bigger, triple an even bigger number is even bigger. You get the idea. The denominator is getting gymongous. It's exploding, while the numerator isn't doing anything to stop it. So this whole thing in this instance is approaching 0. So we've seen sort of 3 different variations, and it actually kind of covers all of our bases for if we're dealing with any rational function. Anytime you've got a polynomial living over top of another, if you take a look back, on the final page of that notes file, there's a theorem that basically says what the limits as we let x approach plus or minus infinity of a rational function are going to look like. And it ends up drawing explicitly on what we would call the degree of the polynomial. If you haven't heard that term before, it's just fancy algebra talk for highest exponent that shows up. And these examples we've seen kind of cover all of the bases. If in like this case, the degree of the bottom is larger than the degree in the top, it's going to end up overwhelming things when it's all said and done, and our limit gets driven down towards 0. If, like in that very first example from the previous video, these degrees are equal to each other, they kind of balance each other out, and we end up with what we call these leading coefficients, the constants that are stuck on those high power terms. If in like the first example from this video, the numerator up here, if we put that cube back in, and it's the thing up top, it ends up being I've heard some people sometimes refer to these as being top heavy or bottom heavy. That can be a useful sort of visual thing. But so yeah, the top blows up while the bottom does nothing to stop it, and the whole thing ends up approaching infinity or maybe negative infinity depending. So sort of the moral of the story here is zero in on these high power terms when you're dealing with this stuff. Okay, so you may notice we got that theorem. It feels sort of like that's like the pièce de résistance that that's finishing off this notion. But then there are a couple of examples right after it because they don't quite fit the mold. So let's take a look at those. But board space, you get the idea. So we can kind of treat these like rational functions, but that theorem doesn't technically apply because of the square root. That's not really a rational function. So anyway, the same principle is kind of still in effect, though. For really large x values, subtracting 2, pretty meaningless. Adding 1, similarly meaningless, even if it's underneath the square root like that. So we can kind of follow that same approach. Let's take a look and see how that shakes out for us. So disregarding the lower power term, we have just a 3x up top, and then below dex, we have 2x squared underneath that square root. That's important. Don't lose that. All right. So now the same idea is kind of in effect. Without the plus and the minus, then we can probably cancel some stuff here. So what'll end up happening? We do this. We have a 3x here, and we can kind of split this up as square root of 2 times square root of x squared, and the square root of x squared, you're probably inclined to say that's just x, and sure enough, cancel those guys like we've done in the past, and we end up getting a limiting value of 3 over the square root of 2. For the record, I haven't explicitly said this. If you're used to having to like rationalize denominators, like rewrite this as 3 times the square root of 2 over 2, you can do it, but I don't require it. This is a perfectly fine number as far as I'm concerned. Okay, so that's one of the 2 examples down, and it's like, okay, well, it still more or less followed what we were doing. We just had to be careful about the power living underneath a root. So what gives? Well, I pointed out. The next example is another one of those really subtle modifications. It's actually even more subtle than the powers. All we've done is put a minus infinity on that guy right there. And what most students will end up doing is, well, they'll say, well, changing that infinity, negative infinity, it's not going to alter much. It's not really going to here either. And, down here. And so they say, well, sure, the limit ends up being the same thing. And they're like, okay, well, Professor Carroll, doesn't it work out the same way? Why did you just erase this is the final answer box from around 3 over the square root of 2? It turns out it's not quite the way this works. So what I'd like for you to do, and I can't, like switch over to a screencast to show you, but take this guy right here, put it in your calculator real fast. Press pause, type this guy in, and then see what ends up happening. All right. So you've probably noticed the issue with this stage. So the graph on the other side of the y-axis, where you have negative x values, the graph is underneath the x-axis. Your function values are negative, and if you look at it, it doesn't look like it's ever getting anywhere near going back over the axis. So having a positive limit doesn't make much sense. So it's kind of a subtle thing, and it comes back to the, it feels natural to say it, but it ends up being awkward in practice. What's going on here is if x is negative, squaring it makes the thing positive, right? You lose the minus sign. And then taking the square root, it doesn't actually drop you back at x. it actually drops you back on the absolute value of x. And so if you work through the algebra here, remember x is negative. The absolute value of something that's negative is negative x. So we have a minus sign that ends up popping up. And in practice, that ends up telling us that our final answer is in fact the negative of the thing that we came up with before. So be on guard about that when square roots come up. It's really easy to, if for a positive infinity, it didn't actually have any impact. It's if it's negative that you end up with some kind of issue. So, be careful there. One thing I do want to mention in closing, because this is one of those like tricksy math professor things, you'll notice in the examples I've presented here, I've always conveniently listed the highest power terms in front of these things so we can readily identify what's going on. Again, math teachers are devious, and they won't always write these things this way. You might end up seeing something like this thing is flipped and have negative 2 plus 3x. Always remember to look for the highest power term, not just the one that's written first in this expression. So be very careful with that. Every now and again, students will slip up on that, and it's like, oops, insert Yu-Gi-Oh joke about trap cards. All right, so that's what I've got about limits. So, once again, congratulations, you have unlocked a trophy. Chapter 1 is complete. So now that we've built up our notion of what a limit is, we're actually going to delve into the meat of like why our calculus ended up, coming up with this stuff and why these limits end up being important. So that's coming up in chapter 2. So, again, thanks for watching. I don't know. I said thanks for watching in the last one, but I, raised the pitch of my voice at the end, so it sounded like a question. No, I mean, really, thanks for watching.